in. So today it's my great pleasure to introduce Professor Ken Burch from Boston College joining us today. Ken is a really well-established expert on 2D materials in both topological and correlated quantum materials on a variety of experimental techniques, including but not limited to optical spectroscopy and novel transport techniques on heterostructures. His work really spans the whole spectrum of quantum materials from high TC cuprates to the iron pnictides, to quantum spin liquids, to topological insulators, direct semi-metals, to 2D TMD materials, and also the recent 2D magnetic materials. Ken obtained his Bachelor of Science degree from UC Santa Cruz and his PhD at UC San Diego, both in physics. And he then went on as a director's fellow at Los Alamos National Lab before becoming an assistant professor at the University of Toronto. He moved to Boston College in 2013 and has been promoted to full professor earlier this year. And Ken has won numerous awards, and some of which include the Ontario Early Researcher Award and the Ashraf Richardson Award. So I think he has some really interesting recent results, which he will show us. And without further ado, so Ken, the floor is all yours. And if you have questions, you can feel free to ask or type in the chat. I will keep an eye on that. So.
Oh, good. I was worried this was gonna be like teaching, where I was gonna have to do in person and remote at the same time. But anyway, thanks, Ming. I really appreciate the very kind introduction, and it's been good to see some old friends and catch up. So today I want to tell you a little bit about the work we've been doing in my group for a number of years now, trying to sort of find evidence for and figure out how to measure the presence of non-trivial topology. I would say that actually the group works not just in van der Waals materials, but I'm going to today focus on cleavable systems. And sometimes I like to call this the endless search for Majorana, for reasons that'll become clear. So in any event, I'm going to start there we go, sorry. So I realized that it's almost lunchtime where you are. So if you need to leave early, I will understand. So here's the kind of 5-minute version of what I'm going to tell you. So I'll start by telling you sort of how I got interested in topology and materials, and in particular what we mean by that, right? So namely the idea that you can have this geometric way of understanding sort of wave functions and the way they evolve, and that this can have real physical consequences, and in particular in terms of introducing new phases of matter. And of course, one of the kind of challenges whenever you have these new phases of matter, especially when they're driven by topology, is how to detect their existence, right? So there's not a clear broken symmetry, and so often the way one goes about that is by looking for their new excitations that are a product of that new phase. And so one of those oh, sorry, I spent too much time in California. I mean, one of those excitations that you can find is a Majorana fermion, which is a particle that is its own antiparticle. I think I'm not going to spend a lot of time explaining what a Majorana fermion is, but the key idea is that you can have these kind of new excitations that are fractional in some way, be it a spin-on or a fractional charge, that really is evidence of the fact that you have this new phase of matter. And so we've, in my group, been using various techniques to try to look for that in a couple of different systems. So the first system that I'll tell you about is a kind of new way of looking at this topological business that emerged in the last 3 years. So one of the kind of key signatures that you can have of a topological phase is the so-called bulk boundary correspondence, where the non-trivial bulk leads to new modes at the boundary. And typically we think of this as, say, surface states on the surface of a TI, but it turns out under the right conditions, these states that emerge can then be gapped out, and you can get actually even lower dimensional modes. So in other words, rather than getting, say, a 2-dimensional mode on the surface of a 3-dimensional system, you can actually get a 1-dimensional mode. And this is evidence of the fact that you have the so-called higher order topological phase. So the idea here is that the boundary that you're interested in is not 1 dimension lower, but 2 or 3 dimensions lower than the bulk, and could only again exist on this kind of lower dimensional surface of a bulk system. So I'll explain to you why we believe that these iron-based superconductors may actually be a good system wherein this can emerge. And it's really this kind of coexistence of this so-called S plus minus order end of non-trivial topology at the same time that in the superconducting state will give you these 1D hinge mode. So to try to prove that, my group looked at this iron telluride selenide, and this is a picture of one of the devices we made that I'll show you, where the purple is FTS, which is meant to be one of these higher order topological superconductors. And then the sort of yellowish bits are the contacts. And then the greenish part is actually an insulator HBN. And the purpose of this HBN was to cover up the hinges on one side such that we can make identical contacts to the two surfaces, where one of them touches the hinge, that's the one on your right, and the other sets touch just the bulk. And what I'm going to show you is that with the idea that the contacts that touch the hinge should therefore see enhanced conductance due to this additional mode that's sitting there on the hinge, whereas the ones that touch the bulk would just look like normal Andreev reflection. And indeed, what we saw is from the contacts that touch the hinge, when we measure the differential conductance versus voltage, we see an enormous zero bias peak that shows up in the superconducting state. And we take as evidence of the fact that there is indeed this hinge mode there in this system. So I'll then change gears and tell you about a different van der Waals system that is meant to follow a model where topology can emerge from the spin sector and not from the charge sector. So here we're interested in what's called the Kitaev spin liquid. So here you have a spin 1/2 on the honeycomb lattice, and the bonds, which I've artificially colored blue, red, and green, essentially have an icing-like exchange, but of a particular component of the spin. So for example, the X component is exchanged along the blue bonds, the Y component along the red, and the Z component along the green. And so this is a highly frustrated system, but amazingly, it can still be solved exactly. And its ground state is a spin liquid where you have Majorana excitations. So essentially, you can think of these, as I'll explain later, as your magnons have been fractionalized into fermionic excitations. So I'll explain why this particular material, lithium chloride, might actually give you this kind of a ground state. But the key point that we wanted to see if we could find was, can we find directly the fact that it has these fermionic excitations and Fermi statistics? So we spent many years working on that, and I'll explain why we chose to use Raman spectroscopy. But basically, it's an inelastic technique where you can measure the energy and temperature dependence. And what you're seeing here in color is the Raman response as a function, again, of energy and temperature, where red is enhanced and green is meant to be lower. Okay, and so you see this broad series of excitations, so you don't see anything well defined, but it exists up to fairly high temperatures, up to about 100 Kelvin. But what's interesting is if you look at the statistics, so you can basically entirely explain the energy and temperature dependence just by using Fermi statistics. So these contour lines here are the predictions of just standard, what you would see with standard fermionics. And so we take this as pretty strong evidence that indeed you do have these fractional excitations. And as I'll show you, surprisingly, they follow fairly well the pure Kitaev model. But we can also sort of see evidence for where the non-Kitaev terms come in and so on. So then if I have time at the end, I'll briefly tell you about some new work that's been going on in the group, which is slightly orthogonal, but not exactly. So we found out that this ruthenium chloride, beyond having very interesting magnetic interactions, also has another kind of remarkable property, which is it has this extremely deep work function. So its work function is 6 electron volts. And I'm comparing it here with a variety of other 2D materials. But it's not enough that it has this deep work function. It also has a very small gap because it's a relativistic mod insulator with a very narrow conduction band. And so what that means is if you put monolayer graphene on top of it, you will have an enormous amount of charge transfer. And even more remarkably, its work function basically aligns with that of HBN, so that if you put HBN in the middle, you can still get an enormous amount of charge transfer. And so you can really do this kind of remote doping introduced into 2D materials that until recently only existed in, say, MBE. Of course, this also opens, I think, a series of new kind of interesting questions beyond the device implications, which is, for example, now this might give us a new way of doping this cation spin liquid and also introducing strong broken inversion. And so how does that affect the magnetism, et cetera? Another aspect is in my group, we've been for many years developing new ways of doing fabrication inside an inert atmosphere. So we have what we call a clean room and a glove box, where we can do all of our fabrication inside this glove box, not just the 2D heterostructures, et cetera, but we've recently added a new capability, which is what's called a vacuum suitcase. So we can actually transfer materials in and out of the glove box using this vacuum suitcase. So we can take from MBE thin films, combine them with the best of exfoliated materials, and then also transfer them back into a variety of other surface sensitive techniques, including our low T realm. So that's basically the overview of the talk. Thanks, I'm done. Just leave now. Sorry, the jokes only get worse as time goes on. Okay, so I want to introduce sort of how I got into this field. And actually, it goes all the way back to when I was a graduate student. So I was working with Dmitry Basov. We were doing spectroscopy. I was actually working a lot on quantum critical systems at the time. And at the time, actually, funny enough, Dmitry was mostly known for his work on the cuprates. So for those who are maybe less familiar with the cuprates, so these are, you know, you have these 2D planes of copper and oxygen, and as you if you start in the ideal case, they're antiferromagnetic insulators, and you add holes, and eventually they become a Fermi liquid. But along the way, this very high temperature unconventional superconductivity emerges. And so in my group, we were interested in understanding, you know, new ways to kind of tune these materials. But the key point I just want to make clear is, of course, this is all essentially you know, a set of phase transitions that happens through broken symmetry, right? And one of the ways it manifests itself is, of course, that in the metallic phase, your fundamental excitations are just normal fermions. They're just charge excitations. And of course, in the superconducting phase, instead, they are Cooper pairs, right? And so at the time, we were very interested in how to, you know, better understand and control this phase transition, and then understand the excitations that emerge. And that actually is what got us started, believe it or not, in exfoliation. So unlike others who were smart enough to start with something simple like a carbon, we started with something very complicated like Bisco, and we made some progress sort of in showing how various properties of Bisco would evolve as you exfoliated it. And again, what we liked about this exfoliation was the idea was it was a way to naturally tune the dimension, maybe gate it, add in heterostructures, et cetera. But nonetheless, I was in Toronto at the time, as Ming mentioned, and as you may know, when you move south from Canada to the U.S., it's very difficult not to get heavier. And I'll try to convince you that that move to heavier materials was actually quite useful, and in particular was also related to our, along with of course many others, interest in evolving from, say, symmetry broken phases to topologically broken ones. So let me just explain sort of what I have in mind when I'm talking about topology in materials. And there are many different people who are involved, I think, in the development of all this, but I'm just going to focus on say, Michael Berry and the way he described it. So one question you might ask is, okay, I have, say, a particle, it could be charge, could be magnetic excitation, right? Anyway, it's moving through my system. And of course, we all know from quantum mechanics, as a result of its motion, it will pick up some phase. And until, I don't know, the last, say, 20, 30 years, it was thought that this phase was essentially irrelevant because you could always gauge it away, and it was dependent on initial conditions, et cetera. And the insight that Berry and others had was to consider a closed path, right? So where the the particle returns to its initial conditions, and to ask, does it still acquire a phase? And it's actually still pretty remarkable to me that it's actually, you know, with very few assumptions and just using essentially Schrodinger's equation, you can very quickly show, and I'm not going to derive it for you now, but that indeed that it can pick up a phase, which is just this integral of what we now call the Berry connection, and that this Berry connection has a very simple mathematical form, which is, you know, basically just the expectation value of the derivative of the wave function with respect to whatever parameter space you're moving through. So in my case, because we're dealing with condensed matter, I'm going to pretty much just focus on the derivative with K, but of course it could be something else. So if you're in spin space or some other Hilbert space. Okay, so this already starts to suggest that there is a quantum geometry involved in all of this, which is, of course, you're taking the gradient, right, the expectation value. So if I think of, for example, a sphere, it's sort of like asking locally, what is the little, how does the wave function evolve if I move left and right in this phase space that I'm interested in. Of course, if we want to think about topology and geometry more seriously, we should think about a curvature. And indeed, it turns out that Berry defined what we now call Berry curvature, which is this curl of the Berry connection, which again is just the curl of the gradient. Okay, so this is really like asking, again, in this curvature language, literally how is my slope evolving as I move up and down, say the slope from left and right. Okay, and we know that, for example, if I take my sphere and I squeeze it, then locally I will change this curvature. But if I integrate this curvature over the whole sphere, I'll get this so-called Gauss-Bonnet number, which is just 2. And if the reason it's 2 is because, of course, if I take the rings and I kind of go all the way down to the top and the bottom, there would be a divergence. And it's these 2 divergences which give you this Gauss-Bonnet number. Okay. So it turns out you can, again, just apply Stokes' theorem, and you find that you can recover the Berry phase in terms of just this integral of the Berry curvature. And so it's starting to look like this Berry phase is behaving like this Gauss-Bonnet number. Now, where this topology business comes in is to ask, what if I take the sphere, okay, and when I squeeze it, it's straightforward to see how I have a one-to-one mapping, right? Every point on the sphere, right, can be mapped to every other point if I just squeeze it. However, if I squeeze a little too much and I poke the hole, right, there's no longer a one-to-one mapping between the two states, or sorry, the two surfaces. And part of the way you can see that is if you consider the curvature on the outside of the donut or the torus, right, it looks like the outside of the sphere, but of course on the inside, it's not, right? On the inside, you have this 2 different signs of your curvature. And the result of all that is that if you calculate your Gauss-Bonnet number, it changes, right? And so the idea is that you no longer have this one-to-one mapping between these 2 systems, and that is what makes them topologically distinct. So in this talk, I'm going to be interested in materials or phases of matter where really there's no longer a one-to-one mapping, okay? And that's really what we want, is to try to discover such phases and understand where they're coming from. But this suggests that, that this Berry phase kind of acts like one of these topological invariants. It's a way of telling, that indeed there's no longer this one-to-one mapping in your quantum system. And you might be feeling like there's a lot of math, and what does this have to do with real physics? But one way you can see that is in the following, that this Berry connection looks like a vector potential, right? Because the Berry curvature is the curl of that thing. And indeed, if you write down the equations of motion, you'll find that the Berry curvature behaves just like a magnetic field in momentum space. And this is how you can get things like anomalous Hall effects. I don't have time to talk about it today, but one of the things we've been very interested in my group is looking at Berry connection with a different perspective, which is that, of course, d by dk written in momentum space is really just the real space operator. So really, Berry connection is like asking, on average, in your unit cell, where is your particle, right? So where is this state? Okay, so Berry connection is actually directly connected, sorry, pun intended, to this, to something kind of very physical, which is where are we in real space? Okay, so that sort of suggests one way to understand these topological phases. So for example, we're used to thinking of band structures as being, basically constructed from the atomic orbitals of our original atoms and just adding on this, in some sense, this block term. But if you can imagine turning some crank in your model such that you mix up the states, for example, and create a ferroelectric, right? Where now your block state, it's not a one-to-one map back to the atomic limit, right? And so it's this sudden change of a one-to-one map back to the atomic limit that no longer exists, which is one of the ways to think of this new topological phases that emerge, all right? So of course, a challenge in such a thing is, how do you find the fingerprints of such new phases as they show up? And perhaps the bigger challenge, which I'm used to, is what's the right platform for finding these new phases that you're interested in? And so I'm going to show you sort of two examples where my group has pursued different kinds of platforms for these topological things and how we've tried to find evidence for them. Okay, so the first one that I'll talk about is this evidence for hinge modes. Okay, so to explain that, let me first state that, of course, it was also inevitable when I moved to the US, since I moved to Boston College, which is a Jesuit institution, that I would pursue a higher order. But let me try to convince you that it's also interesting in a physics perspective. All right, so to do that, let me show you a different way of thinking about a TI from what I think is often the way it's often explained. All right, so imagine I have a system with two atoms, and I want to keep inversion just to keep things simple, but it's not necessary. In any event, so this could be gallium arsenide or silicon or whatever, two distinguishable atoms where, say, my conduction band comes from atom 1 and my valence band, roughly speaking, comes from the states of atom 2. All right. So even if I was an insulator, it's clear that most of my electrons, are sort of sitting around atom 2, right? At least the valence electrons. And now let me turn on some interactions, say spin orbit coupling or pressure, whatever you want, right? And I bring these two states together and they mix and hybridize. And then I reopen my gap. Okay, so what you'll notice has happened is electrons have physically shifted from sitting mostly around atom 2 to now being partially sitting around atom 1, right? It's almost like I've made a ferroelectric. Of course, I haven't, because I have inversion symmetry, right? But nonetheless, this is no longer, these states that are sitting in this valence band are no longer mappable back to the atomic limit, right? Because they've now physically moved, right? It's like I've shifted the charge, okay? And it turns out that indeed, in such a scenario, if you were to try to calculate some topological invariant, you could find that indeed you had this non-trivial topology. Your Berry connection had kind of gone through a divergence, if you will, right? So if I had broken inversion, then what I would have done is made a ferroelectric, right? And in fact, it turns out you can model ferroelectricity with Berry phases. I'm not going to talk about that, but it works. But nonetheless, if I had a ferroelectric, right, I would expect charges at the end of my dipole. And in the equivalent here, what I get instead are surface states, right? These metallic Dirac-like surface states that show up on the surface of a topological insulator. So now you can ask, well, can I, just like I can have dipoles, I can also have quadrupoles and more complicated things. Can I get even more complicated versions, non-equivalent back, another change that's not mappable back to the atomic limit? So one way you might do that is to say, well, can I gap out these surface states? And so, for example, if I apply a magnetic field in the plane, I would, just shift these Dirac states. With the Zeeman energy, it would look like I'm moving the Dirac point, but nothing really that exciting. However, if I apply the field out of the plane, of course, what happens is then I can mix the states and actually open a gap, right? And so the top surface would disappear. Now, the side surfaces would stay around because, of course, now the magnetic field projects into the direction of the spin for those surfaces, and so they don't get gapped. So I can go one step further and imagine, instead of applying an external field, imagine I have a proximity field, right? So I put magnets on in some complicated way, or I have some complicated magnetic order inside, such that the magnetic field at the side surfaces points, let's say, into the plane. And so now I can gap out both the top surfaces and the side surfaces. But there's a catch, right? And the catch is that these gaps have a sign associated with them, which is, how do I put this magnetic field? Do I put it, along the c-axis or anti-parallel to it, right? And so I can think of it as having a positive gap on the top surface and a negative gap on the side surfaces. And so the result is, it must be that at the boundary of these two domains, namely the so-called hinge, I'd have a one-dimensional zero energy state, right? Which I basically can't get rid of. And that zero energy state is really like a new version of the bulk boundary correspondence, telling me that I have a new kind of topological system. So if you want, you can think of it like, what I've done is to go from the atomic limit to a sort of a Berry dipole. That's not the right words, but anyway, to a sort of dipole, and then to a quadrupole. And because now I have a quadrupole, instead of getting, surface states, I'm getting these one-dimensional modes. So this was a nice theoretical construction done by a couple of different groups, sort of in parallel. Amazingly, these photonics people are very annoying. So they, very rapidly, both in photonics and acoustics and even in electronic circuits, were able to generate sort of equivalents to this Hamiltonian and show that indeed you can get corner modes, which are sort of the zero-dimensional version of what I've been talking about. And so they created a Kagome lattice and they tuned things just right. And then they use speakers to do their version of STM. It's kind of amazing. Anyway, shortly after, there was work by Ali Yazdani's group where he took bismuth, which was believed to be a higher order system, and they proximatized it, and they did various other things, and they claimed to see Majorana as showing up in the superconducting state. I'm not going to make any claims one way or the other whether Ali was correct, but anyway, it's worth noting that this really emerges only on certain sort of hinges of that system. I think some very nice work which came out actually after ours, but was in tungsten telluride, which was also one of the early predicted systems to have hinges, where people used basically Josephson junctions and showed that when they did this Fraunhofer spectroscopy, they could see that there was sort of current being carried along these one-dimensional hinge modes. It only showed up on the right crystal faces. Okay, so I want to tell you about sort of how we have pursued this and why we chose to look at iron telluride selenide. So this requires taking a small step back for those who are less familiar with the iron-based systems. And just to remind you that these are systems where you have hole pockets at gamma and electron pockets at the corners at M. Okay, and it was known sort of, I think, very early on, right, that if the pairing was all intraband pairing, then you would probably just have a multiband S-wave superconductor. But that if you had interband pairing, because you have this pairing between electrons and holes, that you would have what's called an S plus minus, which is to say that you have a change in the sign of the order parameter as you go from gamma to M. Maybe just in the interest of time, I will not talk too much about the various many experiments that have been done, but just to say that I think whether people agree or not that that there is a S plus minus order here, I think it's fair to say that people do agree that it is an anisotropic superconductor and that it is nodeless, that there is no evidence of nodes in this system. Okay, and that will be important later because it's a way of saying that there should be no underivative bound states. Okay. So you have this potential S plus minus superconductor, and it turned out the chalcogenide system is particularly interesting because of its large spin orbit coupling. And so about 5 years after the discovery of the iron base superconductors, there was this very interesting proposal that came from two theoretical groups that noted the following. So they said, look, my conduction band is essentially near gamma, is essentially this pz orbital coming from the chalcogenide. And I've circled it in red to just say that it's of a certain representation, and I put the minus sign to indicate that it's odd under inversion. Then they noted that of course, near gamma, there are 3 d states, so dxy, dxz. They're both even under inversion, and they're of a different representation than the p orbital. And then finally, there's dyz, which has the same representation, but is also even under inversion. So the point was, if you instead of looking in the plane, if you turn your attention out of the plane, then you can have a scenario where as you tune from, say, iron selenide to iron telluride, that you can increase the bandwidth of this pz orbital and also change the splittings with spin orbit coupling. And long story short, along the z direction, you can have this pz orbital come down and cross the first 2 without mixing, creating bulk Dirac points, essentially because they're of the wrong representation, they can't mix. But with the third dyz orbital, it can. And so you can get this inverted band gap, which is exactly what you would want for a normal topological insulator. So this would suggest you would have a topological insulator with topological surface states. What's amazing, though, is, of course, your Fermi level, even if it falls in this gap, would still cross the dxy and dyz bands in the plane at kz equals 0. And of course, you have your Fermi surfaces at M. And what that means is you could have a material where in the bulk, it's superconducting, and you would also have these surface states, and therefore you could get basically, a kind of perfect proximity effect where you don't need to combine materials, you just get it for free. Okay, so since then, in 2018, there was some nice work from Shik Shen's group They claimed to observe these surface states using laser ARPES. They showed up roughly where they're supposed to be. There's evidence that there's spin momentum locking, et cetera, et cetera. I think in fairness, I think there's not consensus in the ARPES community, although maybe Ming can say more about whether this observation is correct. I think it's still quite controversial. But nonetheless, there's also been a variety of different STM works, and I'm sure I'm leaving some out, that have found zero bias peaks inside vortices in this material. And one of the nice things here is that you're sort of in a good limit in terms of being able to observe such things. And this has been seen by now multiple groups in multiple vortices and so on. And there's even a recent observation that suggests that the tunneling into these vortices, into these Majoranas, is quantized as it should be. Okay, so there's reasonable evidence that we have a topological superconductor, but you may have noticed I left out the S plus minus part. Okay, so I want to now ask, what would the consequences be of having S plus minus order and these topological surface states? All right, and I wish I could say we were the ones who thought of this first, but we are not. It was really this Rusheng Zhang, who is a postdoc with Shankar. Anyway, so they said, look, let's say I have these TI surface states, and I have this S plus minus order, right, where the sign of the order parameter changes from gamma to m. That means that, for example, it could be for the surface states on the top surface, they would pick up one sign of the order parameter. And for the states on the side surfaces, they'd be projected out to m, and so they would get a different sign of the order parameter, right? So I would literally have this sign change in the gap of my surface states, just like the construction I showed you earlier for a higher order system. And so they suggested that I should have a higher order topological superconductor with these one-dimensional hinge modes. So the part that I am very proud to say is, even if we didn't think of it first, we read their paper on the archive, and our paper hit the archive 3 months later. So let me show you what we did in the effort to show that this was either true or not true. So we had the following idea. We said, let's take our exfoliated material and imagine it has these 1D hinge modes. Of course, it's extremely challenging to just contact a hinge. But so you might imagine if we were to contact and do point contact spectroscopy, we could see some increased density of states from these hinges. But to prove to ourselves that it wasn't a bulk effect, we would then put HBN over an otherwise identical contact, right? So this HBN would basically insulate our other contacts from touching the bulk, and so they would only touch the, from touching the hinge, and so they would only touch the bulk. And so we would sort of have a built-in control. Right? So we could see if we were seeing enhanced density of states from the hinge, or we're seeing it from the bulk response. And we did all of this inside of our clean room in a glove box, which is what allows us to do all this very fast and with air sensitive material. So we can do 2D transfer like others. We have Raman and AFM inside. So by the way, if you have air sensitive materials, we can help. And then we have a spin coder, a massless lithography, and a depth tool. Okay, enough with the shameless self-promotion of our toys. So here's the cartoon of what we were going for, and here's the actual device. And I'm going to show you data from one, but we have data from multiple devices. Okay, so we have our iron telluride selenide exfoliated here. We put big current leads on just so we could do 4-point measurements and check that it was really superconducting. We put our HBN here such that it covers one of the hinges on one side. And then we have these voltage leads, which we split so we could use them like point contact leads. Okay, so what I mean by that is we would apply voltage, say, from the point contact to one of the current leads, and then we would measure current from the same contact to a different lead. And then we, of course, check that as we played around, if we measured at different leads and so on, that we always get the same response. Okay, and the idea is that it should be that our point contacts, like contacts on, say, the right surface, they're touching the hinge, and so I'll show you the data there. And the contacts on the other surface, they go over the HBN, and so they should only be tunneling into the C-axis. All right. So what did we see? So this is, yeah, please interrupt. Yes, please.
Sorry,
Good.
this is Andre. I was just to clarify, because we can't see your mouse, could you explain again where the contacts are that contact the hinges and whether they're not?
Sorry. Yeah. So good question.
Maybe you are pointing at something, maybe not, but I couldn't see.
No, I wasn't. Sorry. So the idea is that that these are the contacts that touch the hinge, and these are the contacts that don't. So if you were to take a cut through this picture, you would see what I've drawn here. Does that help?
Yes, I think so.
So the reason is that there's this HBN here, right? And that's equivalent to this HBN. So it protects, it's very thick HBN, I should say. It's not thin. So there's no tunneling through the HBN. It's just an insulator that allows us to cover up the hinge and make an identical contact to the bulk. Great, okay. So what did we see? So the data that you see on your right came from this point contact that touches the hinge. And above TC looks totally flat and boring, like a normal ohmic contact. And when we cool down, we see this enormous zero bias peak. And I'm going to say 7 Kelvin, though we've since learned that it was probably hotter for reasons I don't have time to go into, but it was definitely below TC. Okay, and the key point is that we see this enormous enhancement, 17 times. So it can't be just standard Andreev reflection, for example. Now to compare that, our C-axis contact, which by the way had basically the same normal state resistance as the contact that touches the hinge. So there's no reason to think that it's just a crappier contact or anything like that. Now I've zoomed in by a factor of 2 for the DIDV versus voltage, and we see a little feature. If I zoom in by a factor of 10, we see what looks like a zero bias peak, but it's misleading. It's just that temperature is too high. And what you're really seeing is just standard Andreev reflection, where we're just too hot to really see it kind of open up and look like normal Andreev reflection. Okay, and again, that's a 15% enhancement over the normal state. This very large enhancement you see at 20 MeV, we think is just when we start tunneling outside of the TI gap. So we start to see more bulk states and we just get enhancements in tunneling. And then what looks like noise is actually not noise, but I don't have time to explain.
Ken, I'm just trying to understand the units on the y-axis here. So what if I converted this into an actual resistance, what would the number be?
10 ohms, maybe 15.
Okay.
Yeah,
okay.
they're very conductive. We always get very conductive contact. So it turned out, for reasons what we didn't know at the time, was one advantage we have over others is that we're doing photolithography. So it turns out the E-beam damages. So we do photolithography and it seems to protect the system. We can get very good contacts fairly easily.
And I also, so do you have a cryostat inside your glove box, or are you're able to?
No, so that we do quickly transfer through air, but it turns out that that's not such a problem.
Okay, thank you.
Yeah, I'll explain that better if I get to it in the highlights. So you have to be patient. Sorry.
So Ken, is this sorry, naive question?
Please.
All done in a normal phase above TC?
No, this is all below TC. So what you see, the red line, the dark red line on the right-hand side is the normal state.
Okay.
And then as you see the zero bias peak emerging, as it goes from red to blue, it's when we're cooling below TC.
Mm-hmm.
So we never see this in the normal state. And the C-axis data is just at the lowest measured temperature. It's equivalent to the blue line on the right-hand side.
So the crystal orientation doesn't matter, right? I mean, which direction you put these hinges on?
Good question. So, yeah, well, okay. So it should show up when we go from, say, 100 to one of the side surfaces. And it's true that it didn't, we've done multiple devices where it didn't matter which edge we chose. We could see this effect.
Okay.
Is that clear?
Yeah.
And we also did some more controls. So we tried iron selenide, which is not meant to be topological. We actually never even got on Andreev reflection there. I never quite understood why, but admittedly we didn't try that hard. We tried point contact measurements, which also would repeatedly show these nice zero bias peaks. And we think there it's just that when you cleave it, you have many hinges. And so that might be why that when you contact something that doesn't have a nice flat surface, you see this hinge response. And something that I'm quite excited about, which is very recent development, is we've actually been able to get our cryostat. We rewired our cryostat so we could get a bit colder on the device. And also we got better crystals. And we now see something even more beautiful, which is that not only do we see the zero bias peak, we see what looks like perfect Andreev reflection. So we see this kind of flat top that's happening at these low biases, and we think is coming from the fact that we're really tunneling into these kind of chiral edge states of the system. But that's a very new development, so I wouldn't show it to you if we hadn't repeated it in multiple devices, but we don't fully understand it.
But the temperature range is the same as before, right? Previously you got
so the problem whenever you do these transport measurements is that if you don't wire your cryostat well, then you're actually carrying a lot of heat in. So you're not as cold as you think you are in your device, which we didn't know at the time. So this was actually done with, we basically rewired the cryostat with better, anyway, long story short, we rewired it better, do better thermal sinking. So it's actually somewhat colder, and also, frankly, it's the crystals are better. I mean, you can just see it by eye when you cleave them. They're bigger, flatter, beautiful, etc. So.
And sorry, can I keep asking?
Yeah,
Can I
please.
ask one more question?
No,
So
please.
suppose it's not you have a regular, like a normal hinge that some other material that would you see this kind of effect as well? Like that's not partial to the swinging state. One of these
It's not, yeah, it's a good question. So that was actually one of the challenges they had in tungsten telluride, right? Is you should get this. So one way you could think about it is you could think of it like as if your top surface was like a quantum spin Hall, right? Or chiral system, right? And so you would see transport like that. In this case, it's sort of like that, but now with a superconductor. You see, that was actually one of the things that's very challenging here, is because is how to separate what's coming from the bulk with what's coming from the hinge, and we just frankly got lucky that the bulk was not doing anything super interesting when we touched the bulk. Yeah.
So what do you expect the signal ratio between the bulk contribution and the surface contribution? I mean,
Yeah, that's a good question. I don't know the answer at the moment. So we know that the bulk doesn't give us very large enhancement in the conductance when we just touch the bulk. And what we're gearing up for right now is to try to do a series of measurements where we change, the dimensions, so longer along the hinge versus normal to it, to get a better handle on that. So the honest answer is we don't know yet.
Mm-hmm.
Yeah. In fact, one other complication, which has arisen recently, we don't even know how this hinge talks to the bulk, right? So it could be that the hinge itself will do, undrive reflection into the bulk, right? It's not clear that it's really protected from it. So it could be that part of what we're seeing is just the hinge is a very good contact, right? So that's, well, anyway, let me leave it there. So I think
Oh, sorry. The Doug, you have one more question in the chat. Do you want to ask it now?
Yeah, sure. So I'm still a little confused about how to think about these states at the hinge. So
Sure.
How many channels are participating in this? Like in the chiral, like I should get one chiral edge state, say, in an ordinary 2D quantum spin Hall thing at the edge, and that would give me a maximum conductance of something like
3 squared. Yeah. So I know what you're getting at. So here it's helical. We haven't broken time reversal. So there should be 2 of them.
Right.
And it should be something like on the orders of 2e squared over 8. I asked a few theorists and I got slightly different answers, but roughly orders of e squared over h. The challenging thing here is we're not really a point contact. Our contacts are huge. They're like a micron.
Yeah. But I mean, if you're connecting to a single channel is what's propagating along.
Correct. So one thing what I was going to say is it's not clear to me whether maybe I should think of my contact as a few different point contacts. Okay. And then the other problem is that, when we're doing these measurements, there's nothing that prevents the current from going into the bulk.
Sure.
Right. It's not like a fractional, it's not like a quantum Hall state where I know there's nothing in the bulk to be measured.
So in that graph in the bottom right, again, so is that inverse milliohms or milli-inverse ohms? Or?
Oh, I'm sorry. The graph on the bottom right is actually now normalized to the normal state. Sorry.
Okay.
I wanted to show it does go a little above 2, but it basically.
So the conductance in the on, the effective, the 2-terminal resistance in the on state is again still kind of,
extremely high. Yes, we're nowhere near a one-dimensional channel. That's right. Yeah, that's also a part we don't understand. That's right. Because if it were just this onset of a one-dimensional channel that we were seeing, it should be a blip on our measurements, and we don't understand why. In some sense, that's the part we don't understand. Sorry, I guess.
Apologize.
No, please, go ahead. Yes. No, go ahead.
Very naive question. The channels on quantum Hall effect is only limited to fermions, right? So if you have a superconducting pairs, that supposedly one channel should flow like indefinite amounts of current. Is that correct?
So even in these 1D channel systems, right, you typically don't have backscattering allowed because you'd have to break time reversal. Either we've already broken it in your chiral, And it's really the loss comes from when you touch the contact. So it's actually not at all clear here how it works.
No, but I think Hanyun's point is that in principle, you know, this is like a gapless domain between two surface-induced topological superconductors.
Yeah.
Strictly speaking, this is a gapless Majorana edge, and so in principle, what you should really be measuring is the thermal conductance. The electrical conductance, strictly speaking, isn't well defined.
Yeah. Okay. Good point. So the answer to that, though, is that's why you need Andreev reflection. So you can Andreev reflect into these Majorana states, right? And then you are supposed to get perfect Andreev reflection because they are Majoranas. So that's why we were so excited to see this flat top and, you know, perfect Andreev-like spectrum. But you're right. The ideal thing would be thermal.
Okay, got it. Thanks.
Yeah. No, great. These are fantastic questions. Okay, so I think I will do my best to go through the next part, but I might go a little fast, so I apologize. So I was inspired by my little one to also look not just at topologically non-trivial charges, but of vortices and spins. I think, unfortunately, I think I will skip this. Hold on one sec. Let me see if I can skip ahead a little bit. So the kind of system we were interested in is what's called the Kitaev spin liquid. So this is a model that Kitaev wrote down, I guess, 14 years ago now, where you take a honeycomb lattice and you put spin 1/2 on the lattice, but before you do that, you artificially paint, if you will, the bonds. So I've called the vertical bonds here, I'm calling the X bonds, and then the red ones are the Y bonds, and the green ones are the Z bonds. And I'll have this spin 1/2, and then I apply spin 1/2 onto each site. And then I imagine the following kind of strange exchange where I have only the X component of the spin exchanges along the X bond, the Y component along the Y bond, and then the Z component along the Z bond. And this looks like a highly frustrated system, very difficult to solve, unless you're Kitaev, who's a genius. But anyway, so what Kitaev did was to say, look, let me take the spin excitations, which are bosons, they're spin 1 excitations, and imagine fractionalizing them the way you might break up a Cooper pair into, say, constituent spin-ons or fermions. Of course, I don't have enough degrees of freedom to solve the problem, and it's why it's good to be a theorist. So he just fractionalized one more time. Again, he was in California, into what are called Majorana fermions. And there's actually 2 flavors that you get. One of them lives on the bonds and forms a bound state with its neighbors, and the other is free to move throughout the system. And so this is why you would get a system that fluctuates and never actually orders all the way down to 0 temperature, but would be topologically ordered. Okay. In fairness, his model is in an abelian state. It's not really quite topological yet, but anyway, these are details. So of course, as everyone knows, when you're looking for Majorana, it's important to be sure that you got what you paid for. And so that led us to try to find ways to be sure. And before I explain how we went searching for that, let me explain how you might find it in a real material. Okay, so this is an idea due to Jakuli and Kaluan, who said, look, let me take a d electron system, and I would split it by crystal electric fields into EG and T2G. This would give me a natural way where the orbitals would have, different components of the orbital momentum would be paired more strongly or exchanged more strongly along particular directions. Now, if I turn on strong spin orbit coupling, I can further split the T2G state into what's called J1/2 and J3/2 state. And if I have 5 electrons sitting there, then basically the 3/2 state to first approximation is irrelevant, and I have essentially a J1/2 sitting in a half-filled band. Okay, so I start with something with a large bandwidth, and I dramatically reduce the bandwidth by spin orbit coupling. And it turns out, therefore, even if I have very moderate on-site Coulomb repulsion, I can still get a mod insulator. But now it's a mod insulator of these J1/2s. And so it's really a relativistic mod insulator. And what's wonderful about that is it turns out that these J1/2 states you get, they're very directional in a way that you can show that under the ideal limit, which is to say you only have the J1/2, you have a perfect octahedral neighbors, that when you calculate the hopping, it recovers back to exactly the Kitaev limit. So under a very ideal set of circumstances, you could have materials which are these relativistic mod insulators, which is kind of interesting in and of itself. They'd have these very narrow conduction bands, et cetera, but they would also have this bond-dependent exchange. So, so the material that we've been looking at for a number of years now, which is believed to be close to this limit, is the ruthenium trichloride. You have rutheniums on the honeycomb lattice. They are in the D5 state. The chlorines are almost perfect octahedral. They're not perfect. And by the way, it cleaves and exfoliates. So you can imagine getting to a pure 2D limit. The unfortunate thing about ruthenium chloride is it does order. There's some complications to this antiferromagnetic order I'm not going to go into. It orders at around, now with good crystals, about 7 Kelvin. But interestingly, if you look at the inverse susceptibility, you will start to see deviations from Curie-Weiss starting all the way up at about 100 Kelvin, which we now know is basically the Kitaev scale. So at temperatures above the ordering temperature, it does look to be dominated by this kind of Kitaev physics. Now, I don't, in the interest of time, I'm going to skip trying to convince you that ruthenium chloride is a relativistic non-insulator. If you're interested how I know that, ask me later. But let me skip ahead to explaining how we went after these kind of excitations. And we chose to use Raman, and I want to explain why in a slightly unconventional way of explaining Raman. So normally when you think about optics, you have some AC electric field and you're inducing a polarizability, and it's that susceptibility that you're measuring. Of course, that susceptibility can always be Taylor expanded by its coupling to some operator. So I would get two, let's say in the first order expansion, I'd get two terms, just the standard susceptibility plus a new term, which is the susceptibility, the derivative of it with respect to some operator times the fluctuations of that operator, okay? So the first term is the one you're used to. It's how you get absorption, reflection, etc. But the second term is the interesting one, right? So now I have fluctuations multiplied by my AC electric field, and so I should get sidebands, right? So basically, if I have, you know, the sine of omega t, omega 1t times sine of omega 2, I'll get omega 1 plus omega 2, etc. Right? And so this is actually how Raman was first thought of in the 60s. I shouldn't say first thought of, was really discussed in the 60s as essentially a noise measurement, right? That you're really looking at noise coming off of your reflected light. So just to ground things a little bit, you know, it's very natural to have the susceptibility, of course, be coupled directly to the lattice displacement, and therefore the fluctuations you're seeing are just phonons. And what's nice about this way of thinking about it, makes it very clear, because it's the alpha by the operator, right? That your Raman will be essentially, its response is a tensor, right? Because you'll be coupled to both the incoming and outgoing polarizations of the light. It also shows you why it can be challenging, because even in the best cases, it's something like 1 in 10 to the 8 photons that are Raman shifted. And for magnetic responses, it's usually far worse than that. In any event, so we've built up a custom system where we can actually vacuum suitcase. And this gets actually back to Doug's question earlier. So we can vacuum suitcase from our glove box into our low T Raman, which can, by the way, also do transport and photocurrent. So if you have air sensitive materials, we can help in another way. Now, if you have spin orbit coupling, then the operator that couples to your polarizability could be some form of S dot S. In which case, the noise that you're seeing could be magnons or spinons, and that's actually how we see them in Raman. It can also just be the standard thermal fluctuations of your magnetism, right? So what you'll see in that case is like a Debye-Waller factor. When you do X-rays, here what you'll see is a broadening of the Rayleigh line, and that broadening is essentially from these thermal fluctuations. And indeed, we were able to use that. So this is the Raman response versus temperature and Raman shift. And that green you see is not garbage. It's actually the thermal fluctuations from this 2D ferromagnet. And we showed that you could use this to identify the order in 2D materials. Because basically the thermal fluctuations, of course, gap out when you order. And in fact, very recently, that approach was used by Hyung-Sik Chung's group to show that in nickel PS3, it looks like the magnetic order dies when you go to the single layer limit, and it's probably in this BKT limit, which is quite interesting. So I realize this is a somewhat complicated slide, so let me just summarize. Basically, you take your strong laser, every so often a photon scatters and creates some excitation, and your students are forced to wait until they see the data you're looking for. All right, so what did we do in ruthenium chloride? So we wanted to show that the excitations we were seeing were really fractional. So we realized that the response should be basically a joint density of states of these Majoranas times 1 minus a Fermi function squared. And the reason for the squared is, again, that you're you're creating pairs of Majoranas of these in this system. Of course, if you had just normal, say, phonons and things like that, you would have their Raman susceptibility times a Bose factor +1. You could also look at the anti-Stokes, which is where you the photon gains energy. So that's to say that it absorbs something rather than created it, and so therefore you would get a Fermi function squared instead of 1 minus a Fermi function squared. And you would get your normal Raman response of a Raman susceptibility times the Bose function. So we realized that if we take the difference in the data from the Stokes minus the anti-Stokes, we would get the total susceptibility, which is, in the case of the fermionic excitations, would cancel out this NF squared, and we would just be left with 1 minus 2NF, and would cancel out the Bose factors, right, just by taking the difference. So we would really dramatically simplify our analysis. And then furthermore, we wanted to really focus on its temperature and energy dependence to look for this fermionic statistics. And so we wanted to get rid of this 1. So what we did was we went to a temperature where we knew that basically there was no temperature dependence coming from magnetism, and even the phonons were basically boring, which turns out to be about 150 Kelvin. But for the results I'm going to show you, it almost didn't matter. We could choose anything between 100 and 200 and get the same. Okay, so we just subtract off this, this sort of temperature independent part, right? And this is what I'm showing you here. Okay, so the red is where we see enhancements in the Raman susceptibility, and the blue is where it goes down, all right? So the sharp feature you see close to 15 MeV, that is just a phonon, so that's why it doesn't do anything particularly interesting. This broad feature at low energies and temperatures, that's the magnetic continuum, right? Coming from these fractional excitations. And so to prove that they're really fermionic, we basically take the response at the lowest temperature, we multiply it by the appropriate Fermi function, and then we just took cuts at different temperatures, and that's here. So the straight lines are the actual data, and the dashed lines are not fits, but they're just the predictions of what should happen with Fermi functions. Okay, and so we find that the temperature and energy dependence of this continuum is completely described by Fermi statistics, and therefore is consistent with these fractional excitations. Now you may be tempted to say, wait a minute, this is an antiferromagnet. How do you have these fractional excitations? Good question. So part of the answer is that we're at high enough energies and temperatures that the non-Kitaev terms don't seem to contribute. And part of how we know that is we worked with Matome's group, who did the exact calculation for the, did the calculation for the exact Kitaev limit. We take their calculation and subtract from our data. And what we find is perfect agreement, except in of course, near the phonon, because there's no phonon in their calculation, and also in this small little region at low energies and temperatures. And that enhancement in susceptibility, we believe, is coming from the non-Kitaev terms, contributing to the response. And so that's how we came to believe that there's really very strong evidence here that we have fractional excitations in this system.
So I mean, you're looking at gamma point, right?
Yeah.
So if you're looking at gamma point, I mean, so this result isn't, I mean, consistent with neutron scattering result. People claim you have this sort of star-like excitation.
Good question. So first, okay. So actually, so they see a continuum at gamma as well, but they only see it above the Néel temperature. And then when they cool below the Néel temperature, that's when they see the magnons.
Right. But I mean, but most of your measurement is above Néel temperature anyhow, right? Which is like 6-7 Kelvin, right?
Yes, I'm completely above the Néel temperature. That's right. So there's no inconsistency, is what I'm getting at. The difference is that I have the energy and temperature resolution to tell the statistics.
I see.
Right. That's the advantage that I have. The disadvantage I have is, of course, I have no momentum resolution, which I would love, but I just don't have.
Ken, could you
Yeah.
clarify? So in the formulas for the Stokes and anti-Stokes, when you said knowing density of states, it's the density of states of Majoranas, right? Because those are the elementary fractionalized degrees of freedom.
Yep.
And then when you say, so when you multiply it by 1 minus NF squared, where does that come from?
That's just from considering the fact that when I'm doing Stokes scattering, I'm literally creating pairs, and they have Fermi statistics.
I see.
Right. It's basically very similar to what Ming would deal with, except that in my case I create pairs, and so I have the square instead of just 1 minus.
And the reason you create pairs is fundamentally because because
essentially the Raman, you can think of it like the Raman process is flipping a spin. And so it creates a pair of Maronas. In reality, it's actually exchanging spins between different sites. But essentially that's what's going on. Yeah, that part is this, roughly speaking, the same as neutrons.
Right.
So do you actually, yeah, sorry, Andre.
Sorry, so would it be correct to say that what you know, the punchline, if I understood you correctly, is that those elementary excitations, if you didn't know what they were, you might have assumed that they're bosonic. And
Correct.
what comes out from your analysis is that that 2 factor of n times the Fermi function and what comes out indeed from your data, suggesting strongly that whatever these things are, and there are suggestions they are Majoranas, of course, is that they're fermions, correct?
Yeah, exactly. So I cannot tell you with my Raman response whether or not it's fermions. All I can tell you is that it's fractional. That's right. That's exactly right.
So do you actually see a gap? I mean, if you go below Tn?
So we don't. There's another group that has gone below the Néel temperature, and they indeed do see a gap in magnons.
No, I mean a gamma point. I mean,
At gamma. Yeah.
So what's the size?
It's really not. It's because it's not really a 1 magnon. It's a 2 magnon excitation that they see.
What's the size of the gap?
It's that's a good question. I think it's on the order of 1 MeV, but it's been a little while since I looked at their paper. Yeah, maybe 2 MeV, something like that. It's sort of just on the border of where I can measure, to be honest.
Okay, thank you.
Yeah. Okay, so maybe let's see. So I think I'm running out of time, so I will maybe just very, very briefly say 1 or 2 more things, since while we're on the topic of ruthenium chloride. So one of the things we got, I worked on when I was a grad student, another thing I worked on was these so-called digital magnetic heterostructures. And this is a trick in MBE that was invented originally allowing one to see the fractional quantum Hall effect, where you could put the dopants remote from the layer you were interested in. You know, 2D materials are a kind of remarkable set of capabilities. We have a huge toolbox of things we can do, but you know, we are all in academia, and we know the importance of also having donors and acceptors, which is the one thing we don't have in this field. And I want to argue to you that actually ruthenium chloride is such a material. So it turns out that it has this very narrow conduction band with a small gap coming from the fact that it's a relativistic mod insulator, but the ruthenium and the chlorine are also very electronegative. And so the work function is roughly 6.1 eV. If I compare that with graphene, it's at 4.6 eV. And so I expect a large charge transfer from the monolayer graphene into ruthenium chloride, and similarly from bilayer graphene. It turns out that HBN, its valence band lines up roughly with ruthenium chloride, and so therefore you can also get a lot of charge transfer from the monolayer graphene into ruthenium chloride, even if the HBN is in the way, at least cartoonishly. There's nothing special about monolayer graphene. Tungsten selenide should also do this. There is something special, however, about ruthenium. So if you look at chrome chloride, which basically has the same physical structure, it's just a charge transfer insulator, and so actually its conduction band is far, far away, and there is no chance of getting charge transfer from graphene into chrome chloride. So I don't have time to explain how we did this, but basically if you use Raman spectroscopy, there are 2 key modes that are well known in graphene, the G mode and the 2D peak, and luckily they have different dependencies on doping and strain, such that if you plot them if you measure both of them in your material, you can directly determine whether they're shifted from the sort of ideal case by strain or doping or both. And so what you see here in the white are dots where the graphene was sitting on top of just silicon oxide, and we see basically no strain and a little doping. And then when it covers, when the same graphene is then sitting on top of the ruthenium chloride, we see an enormous shift along the doping axis. That's equivalent to roughly a 600 MeV shift in the Fermi level of the graphene. And then to check, we made, of course, heterostructures with chrome chloride, and there what we see is a change in the strain axis because of the difference in the lattice constants, but we see essentially no change along the doping axis. The more exciting thing is, so here I'm actually showing you a map of the G peak, where we put this monolayer graphene over both a single and bilayer ruthenium chloride. And from the map, you can easily see where the ruthenium chloride ends, but you cannot tell when you go from 1 to 2 layers of ruthenium chloride, and that's because essentially all the doping happens in a single layer. We also checked this story with HBN. So indeed, if you put the HBN in the middle, you can still see charge transfer through the HBN. In this case, it was 5 layers, so it wasn't a huge amount of charge transfer, but nonetheless, it was there. And just again, to give you numbers, in this particular device, in the monolayer graphene touching ruthenium chloride directly, we see charge transfer on the order of 210 to the 13. And when we go over HBN, it goes down by a factor of 4, something like that. And we now have, I would say, a little more evidence that you can control this charge transfer by the thickness of the HBN. And I'm not going to show it to you, but as you would expect, because the dopants are remote, you get basically the highest mobility you can possibly achieve in dopings at this level. And what's more, it's extremely short range. So if we take cuts through our Raman data, we find that this doping ends right at the border of ruthenium chloride and roughly within 60 nanometers. And if I haven't convinced you, there was a really impressive blogger who called it very cool stuff. So hopefully you also think this is we're quite excited about it. I think I'm basically more than out of time. So rather than bore you with the other things going on in my group, let me just acknowledge the various people who were involved. First, Mason Gray, who's a fantastic grad student and is, by the way, now looking for a postdoc if you're interested, who did the work in FTS. Samples from Genda, who's been a wonderful long-term collaborator in the usual sources for the HBN, and that work was supported by NSF. The ruthenium chloride was done by another fantastic grad student, Yiping Wang, with lots of theory help and samples from Dave Mandris, and support from ONR, and the WA semi-metals, which I didn't tell you about, then I won't talk about, and thank all these wonderful people we've worked with support from various places, and I didn't tell you about the biosensing, so I'll also skip that. So just to summarize, I hope I've convinced you that topology is an exciting new, well, maybe not that new anymore, but anyway, exciting way to look at different phases of matter, but with the fact that it's so non-local being very difficult to detect. But nonetheless, that we have evidence for this higher order topological state in FTS by looking at these kind of hinge mode responses, and that we can also see this through Raman through the fractional excitation we see in the response in ruthenium chloride. And so with that, let me thank you very much for your attention.
Thank you, Ken, so much. It was a great talk. Any residual questions anybody else has?
Maybe a quick question, Ken. Nice talk. So on the FETSE, so you refer to the earlier LDA calculations for the P-band crossing the Fermi energy along gamma Z.
Yeah.
But my impression that there's some questions that are being raised, whether in the bulk, whether that's really happening, and I don't know whether you've looked into this.
That's a great question. So I think there are 3 problems. Let's see, 2 theoretical and 1 experimental. So the theoretical problem is the DFT gets the Fermi level wrong by I think about 100 MeV. And so it's sort of artificially shifted to match the ARPAs. The second is that I think it doesn't fully incorporate the renormalization that we know happens, the correlated renormalization. So one may also worry about that. And then the final is that there's some recent work by Poroshenko, who claims that this PZ orbital doesn't cross. So I think the safe statement is that the ARPAS community has not come to an agreement about whether this inverted gap actually occurs. I would say with my experiments, it's not clear. So one thing that we were quite excited about originally was that if we saw the hinge modes, actually there's one part I didn't say, which is of course it also strongly argues for S plus minus, right? Because if it's a nodeless system, getting these kind of Andreev bound states is not so obvious, right? But having a topological S plus minus system, it seems straightforward how it would give you hinge modes. And so that's about as close as I'm willing to go, I would say. I would say our experiments do not solve that mystery.
Mm-hmm. Fair enough. Thanks.
Yeah, like great question. Yeah.
TC, you have a question, your hand raised?
Yeah, hi Ken, thank you for the nice talk. So I have a question concerning the first part of the talk. So for the properties of these hinge mode in these high order topological systems, so how are they different from the edge state in the 2D systems?
Yeah, good question. So one, how is it different than an edge state on a 2D system? Right. So they're different in the following sense. So in the same way that, say, the 2D surface states of a 3D topological insulator couldn't exist on a pure 2D system, these 1D hinges are kind of couldn't exist in a 2D system, right? That you really need this kind of 3D-ish thing. But I would say at the end of the day, they're not all that different, to be honest. I think it's just that they emerge. The way I think about them is as domain walls between different topological states, right? But it's what I guess the real question, maybe if I can rephrase your question, is, you know, what physically at the end of the day, other than how they emerge, would be different, right? Like between, yeah. And for that, I don't have a good answer. It's a great question. I don't have a good answer for you. It's not obvious to me, with the one caveat that they can take, let's say, turns in physical space that couldn't, right? So I drew them as only going around the top surface. Actually, maybe it's faster if I do it this way. Right, so I drew, oops, sorry, just ignore the bio stuff. I drew them as, you know, as if they only go around the top surface, but it really depends on the details. So they could instead, they could have gone, you know, let's see, like this. You see what I mean?
Right.
Yeah.
Right.
And I think the real different systems are going to be the corner modes. The nice thing about the corner modes is you can imagine easily cutting things in a way that you could have many of them. Did that answer your question?
Yep, thank you.
Yeah.
Yeah. So I see that Matt also mentioned something in the talk. So let's see if I can rephrase this. Maybe
Sure.
it's the same question in mind or not. So the way, for instance, Liang Fu thinks about the FETSC from his own talks, right, is that it's basically the simplest sort of in situ realization of the Foucault proposal, where you take a surface of a 3D TI and you proximity couple to a superconductor. Except
Correct.
here you don't need to bring proximity, the superconductor is intrinsic.
Yep, correct.
That would explain why you would see the trapped Majorana modes in the vortex cores, for instance, right?
Yep.
Now, what Matt, I think, is saying is that, look, if you could then somehow have two superconductors with different gaps, different phase of the gap, then on the boundary between them, you would have a one-dimensional domain wall.
Yep.
Similar thing, by the way, would happen if you applied field locally, magnetic field pointing up in one domain and down in the other domain, right?
Yep.
And so the question is how important is it that it's 3D? Yes, I get it that you need to have 3D TI to start with, right? And I understand what you said about the hinge modes, but are those hinges really that important? Could you not imagine just taking a two-dimensional surface, just look at it, and it's fully gapped, and you somehow engineer the equivalent of S plus minus by making, you know, half of your superconductor with a phase one way and then the other. Basically, you make a, like, instead of corner junction, you make like a planar junction, right? And what you're trying to do here is not to do it's like Josephson interferometry, but you're not asking about what the superconductor is. You're just trying to see about the main wall.
I think I get your question. Let me see if I can answer it. So I think, well, okay. So here the domain wall emerges from the intrinsic order parameter of the bulk, right? So I didn't have to do anything. I didn't have to put ferromagnets down. I didn't have to strangely engineer, you know, different signs of the order parameter. I didn't have to put together physically two distinct, you know, cuprates, right? The same story. If you take cuprates, cut them the right way. Here, it all comes for free in the same material.
Right.
You know, so I used to joke that this material is like handed from on high. You know, it's like kind of amazing. It's just all there in one shot, right? So if this hinge story works out to be correct, right, I don't have to go through all the pain of, you know, proximity-induced magnetism and superconductivity and, you know, et cetera, et cetera. If I want to, for example, do the Josephson interferometry you're talking about, in fact, here, all I have to do is cut the material, right? I could, for example, you can imagine cutting a hole in the center of this material, and now you have a hinge on the inside and a hinge on the outside. You know, you could cut paths in whatever way. And so this is actually some of the things we're thinking about doing next is for example, what if I put magnets in the path? So I would say, if you want an answer in terms of how are these hinge states physically distinct from the ones you would get at the edge of a quantum spin Hall superconductor that's quantum spin Hall system that's been made superconducting, I don't have a good answer for you. Except that the kind of experiments that I can now do with this system, because it's all intrinsic, I think are far better. Better is maybe the wrong word, but you know, it's just going to be a lot easier, right? It's like, for example, you know, the 1D wires, right, have been extremely difficult to work with and make, you know, these Majoranas at the ends and show that they're there and et cetera, right? Like if you could, for example, turn this system into an even higher order system where you had corner modes, you get it for free.
Yep.
Do you see what I'm saying?
Yep, yeah.
So it's a great question. I have to think some more about if there's something intrinsically different about these hinge modes. But at least as an experimentalist, there's something very nice to work with.
Mm-hmm.
And you know, I would say, of course, the thing I said earlier, which is they maybe teach us something about the order parameter that's very difficult to establish otherwise, which is this S plus minus. Although I admit that I'm not at the moment taking an opinion about S plus minus, but except that if it's there and the hinges are there and real. But anyway.
Ken, is there any plan to actually do thermal conductivity in these things? Because as you're probably aware, there's still a big problem with all these Z2 TIs that are supposed to have ballistic edge states that don't actually behave ballistically except over very short distances.
So the short answer is yes. We are collaborating with someone who is going to try to do thermal measurements. As you can imagine, it's going to have to be something local, like not a standard thermal measurement, right? You want to see that there's a difference, at least at the edge, let alone hinge from the bulk.
Yeah.
But the short answer is yeah. We've started up a collaboration with someone who's trying.
I see.
So, but who knows? We'll see. These things are not easy. So, but yeah, it's we've also thought about maybe doing photothermal as another way of getting at that same issue, but we haven't started yet.
If there are no more burning questions, maybe like can take a break. We have another afternoon of discussion. So thank you, Ken, very much for giving us a great talk.